your zombie outbreak lab is due. If you were in, no, find a seat. If you were in mods 1 and 2, something that did not get to you for information is not a big deal. I need your percent error as well. So whatever one, I think we all agreeing which one the antidote was. Maybe not, alpha, delta, or tango. But you're based off of the idea that the goal of the antidote was to be 0.2 molar, right? Because we had found out that to be most effective, it was going to be half the concentration of the original sample. Okay, so what I need you to do is calculate your concentrations. You should have 3 concentrations written down. I should see 3 calculations from your y equals mx plus b equation. You are solving for x. You are plugging in for y already because that is your absorbance. You're using the recorded absorbance and you're plugging it in for your x, which was your concentration. Somebody came in and was like, I don't get it. My numbers are exactly the same. Awesome. Like they shouldn't be like really far off. Just the issue is that maybe reading the graph, the sensitivity of the graph was off a little bit. Okay? So I'm making this up. Maybe your data from your device said 0.197 and you calculated as 0.199. Terrific. Whatever one you think is the antidote, then you need to plug that into percent error. Remember, it's what it should be minus what you did over what it should be. So it's 0.2 minus whatever your value is over 0.2. You can't have a negative. I'm expecting very small percent errors. You should have very small. If you have a large percent error, I would have a little sentence following that up. My guess, sloppy lab technique. You made solutions that were not very accurate. Like maybe that one, we actually didn't do very well on a few of them. We knew it. If it's accurate, then you should feel good that you made really accurate solutions. Okay. Tuesday, we have, optional review after school on Monday. If you would like to make it. And then Tuesday we have our test. And today's our last big topic day. So I gave you 2 sheets. If you could take out the first one that says periodic trends on it, please. Okay, so on your sheet, we are jumping in overdrive here. Please stay with me. We good? Okay, so there are 5 trends. These things you all learned last year. I'm going to focus on the 2 biggest ones today. So what I did is I already typed in all of the trends and the definitions for you. You have to kind of remember the ideas of atomic radius, and then there's about 3 other really important ones. But we're gonna refer to this sheet. So I'm not going to go into it at the moment, but we're going to refer to the sheet. The big sheet is the other one that says ionization energy and atomic theory. That's what we're actually be writing on. So this one is a reference. Okay, and there's a bunch of imagery that I will talk about, and it's something that is related to you. But the other one is actually going to be our activity. All this is related to electrons, related to where they are, how they're held on, what it takes to remove them, or what it takes to add electrons. Okay, so electrons deal with energy and wavelength and all that other stuff when they are released. So I thought this was really cool to start off. Maybe you know this, but most people do not. This is all about electrons. So sit back and learn something that you may not have really realized before.
Take a look out your window. Put on your glasses if you wear them. You might want to grab a pair of binoculars too, or a magnifying lens. Now, what do you see? Well, whatever it is, it's not the multiple layers of glass right in front of you. But have you ever wondered how something so solid can be so invisible? To understand that, we have to understand what glass actually is, and where it comes from. It all begins in the Earth's crust, where the 2 most common elements are silicon and oxygen. These react together to form silicon dioxide, whose molecules arrange themselves into a regular crystalline form known as quartz. Quartz is commonly found in sand, where it often makes up most of the grains, and is the main ingredient in most types of glass. Of course, you probably noticed that glass isn't made of multiple tiny bits of quartz, and for good reason. For one thing, the edges of the rigidly formed grains and smaller defects within the crystal structure reflect and disperse light that hits them. But when the quartz is heated high enough, the extra energy makes the molecules vibrate until they break the bonds holding them together and become a flowing liquid, the same way that ice melts into water. Unlike water, though, liquid silicon dioxide does not reform into a crystal solid when it cools. Instead, as the molecules lose energy, they are less and less able to move into an ordered position, and the result is what is called an amorphous solid. A solid material with the chaotic structure of a liquid, which allows the molecules to freely fill in any gaps. This makes the surface of glass uniform on a microscopic level, allowing light to strike it without being scattered in different directions. But this still doesn't explain why light is able to pass through glass rather than being absorbed as with most solids. For that, we need to go all the way down to the subatomic level. You may know that an atom consists of a nucleus with electrons orbiting around it, but you may be surprised to know that it's mostly empty space. In fact, if an atom were the size of a sports stadium, the nucleus would be like a single pea in the center, while the electrons would be like grains of sand in the outer seats. That should leave plenty of space for light to pass through without hitting any of these particles. So the real question is not why is glass transparent, but why aren't all materials transparent?
I like that.
The answer has to do with the different energy levels that electrons in an atom can have. Think of these as different rows of seats in the stadium stands. An electron is initially assigned to sit in a certain row, but it could jump to a better row, if it only had the energy. As luck would have it, absorbing one of those light photons passing through the atom can provide just the energy the electron needs. But there's a catch. The energy from the photon has to be the right amount to get an electron to the next row. Otherwise, it will just let the photon pass by. And it just so happens that in glass, the rows are so far apart that a photon of visible light can't provide enough energy for an electron to jump between them. Photons from ultraviolet light, on the other hand, give just the right amount of energy and are absorbed, which is why you can't get a suntan through glass. This amazing property of being both solid and transparent has given glass many uses throughout the centuries. From windows that let in light while keeping out the elements, to lenses that allow us to see both the vast worlds beyond our planet and the tiny ones right around us. It is hard to imagine modern civilization without glass. And yet, for such an important material, we rarely think about glass and its impact. It is precisely because the most important and useful quality of glass is being featureless and invisible that we often forget it's even there.
Electrons and absorbing that energy and being at the right energy level. Okay, so we've been learning a lot about electromagnetic spectrum so far. You should have a very good idea of what the waves are in size. Like this is very small, that's very large. Because of that, the frequency is greater, right? Because there's more of them. And then the biggest thing for me and for you should be about the energy. Okay, and hopefully we can relate it to some ideas that we know. Like if gamma ray is out of your realm of just normal comprehension because that's something that we don't deal with every day, X-ray should be. And you have to wear like a lead apron to protect yourself because it has high energy. You don't turn on WIXX and be like, oh, hold on, I got to get on my radio suit. I don't have to worry about that kind of energy. So you are responsible for having a general idea where these are, not exactly knowing the precise number. So if I give you blank regions like I did on your first worksheet, you should be able to fill them in. I fully expect that you should be able to do that, okay? With that, we use some equations. All of these will be provided. Again, chemistry is not about memorization, it's about application. Can you utilize this? What is that? Velocity. This has a joule in it. So that has to be in kilograms. Joules, kilometers. Joules has a hidden unit of kilograms. You have to keep carrying that through. Kilograms meters squared over second squared is not what you need to know. You just need to know there's a kilogram hidden in a joule. So that means that's why I need the kilograms. You got to have that recognition. And then this one we'll work on a little bit more, but simply this is always going to be 1. This is the atomic number of if you ever say Z, It's atomic number, and we can only apply this to hydrogen. Anything more gets too complicated. But what this shows is the amount of energy levels it takes to move an electron from one level to the next. All right, so if you'd like, you can make extra notes on the first sheet I gave you. I want to give you a little quick, like AP synopsis, and then we're going to apply things to the other sheet of just the important trends. These trends are so important. So atomic radius, there's actually a picture there, but I have the image as well. First, atomic radius, there's an image on the middle that shows two Br atoms. You see that? It has a 2R. See that? I hope this makes sense, and if you remember this from last year or not, is that when you do something that is circular, or the diameter or the radius, we'd all say, well, you just take it from the outside to the middle. Yeah, of course. That is when you actually have an idea of where the outside is, which this even is a little squishy, so it's not perfect. But an atom is an electron cloud. That's actually the size. So if you ever, hey, do you remember those, remember where you were on the night of April 17th? You're like, I'm a little cloudy on that. You're like, oh, great, so you remembered exactly. No, it's fuzzy, it's not precise. So what we do is we take, and this has come up in questions before, you take the distance between the nuclei, the only solid part of that atom, and then you take half of it. It's got to be the same atom, so then you get a space, or an actual distance. These are the words I need you to know. When we go across, why people have a hard time understanding why it gets smaller is because, well, wait, it gets larger. You're gaining protons, you're gaining electrons. Yeah, you are. But the problem is you're on the same energy level. This is your money term right here. Your nuclear charge is getting larger. So wherever you want to write this, on the upper left there's a atomic radius, or by the actual image. The way to explain why something is getting larger or not is about nuclear charge when it's going across. Your protons are like fortified in this military bunker, which is your nucleus, and it's not moving. So if you gain more and more charge, that is going to be able to suck in those really light, basically massless electrons, and it will shrink that cloud. So nuclear charge, big. When I go down a group, why does it get larger? This one's usually more obvious. What am I gaining every single row? I'm gaining electrons, I'm gaining protons, but the bigger deal, I'm gaining energy levels, right? I'm gaining energy levels. And you might want to jot this part down, though. Every time you gain an energy level, we're going to apply all this today. You're gaining all this other stuff inside, which is called the shielding, which I have a definition on there. But that shielding diminishes that attraction from the nucleus to the outer electrons even more. So let me try to say the biggest statement I can, because you're going to have to write this in a couple minutes. Bless you. These questions will come up in May. Bless you. Why is something larger? Why is something smaller? Why is the electron being held? None of it has to do with wanting to do something. It's an atom. It's not a person. It doesn't want something for its birthday or for Christmas or for Hanukkah, whatever. It is simply about the distance the outer the outer electrons are to the inside, which is the nucleus, that attraction between them, and then you relate it to that situation. So how far am I away? How close am I away? How strong is that attraction? Nuclear charge, energy levels, shielding effect. These are the things that we're going to use as a tool to be able to describe a bunch of different phenomena that we're going to discuss today. And I'm going to hit all the big ones that I've ever seen on these tests. Okay? So the radius is the most important thing. Nuclear charge, energy levels, shielding effect. Okay? And it could be about distance as well. The further you are, the harder it is to hold on to something. All right. Ionization energy is the other really important trend. Ionization energy is the energy required to remove an electron. What you have to make sure you understand is if Megan wants her water back, if it takes her more energy, would it be more difficult or easier to get it from me if it took her more energy to do it? It'd be more difficult, right? Now, I have good defense, because if she starts coming at me hard, I just fall to my back and I grasshopper kick her. That's my defense. But it's all about the size of the atom still. So we're going to talk about that and relate it. If Eddie Lacy ever comes back, hey, we picked up a new running back last night from Seahawks. Maybe he'll run like this down the field, and then we'll cut him in a week. But if he tucks it away, he'll hold on to it easier because he has the ability to hold on to it tighter because it's closer to him. Same idea with the nucleus to the electrons, and we're going to relate that today. But you decrease down due to the distance, right? The further you are away, the attraction force is less. And also why? What else helps? What weakens that attraction force besides just the distance? What's another trend? We just talked about it last one. What's in between? What's the term? The shielding? The shielding effect blocks and diminishes, weakens that attraction force. I know we learned this a little bit last year. I'm not assuming that we have it all down, but I'm talking about the two big ones that we need to know today. Why does it increase going across? It's getting smaller. Nuclear charge. The electrons are getting closer. All those things. Right? As I move across, if you want my plus, every time I move to another atom, it's getting closer and closer to me. It's getting closer and closer and closer to me. If you look at your atomic radius picture, they're getting smaller. The electrons are getting closer to that nucleus. And not only are they getting closer to that nucleus is getting bigger with protons. So it's getting more and more difficult to remove that electron. Okay? So these are the things that really relate, not to this chapter, but really to this level of chemistry. It's the size of the atom and the difficulty to be able to remove that electron. And they are from nuclear charge, distance, the aiding effect of shielding effect. Okay? So, I'll come right back. All right, so what we're about to do, I'm going to mix you up a little bit. I used to do this with a whiteboard, but I realized that people had to write it on their sheets anyway. We're going to do a little exercise about talking about some of the different things on that other sheet. And I want you to be able to kind of talk in your own groups. So, it doesn't matter where you move. I have in about 8 different groups of 3 or groups of 4. If you're a group of 4, you can either sit above and below. If you're a group of 3, just sit right next to each other. But I'm going to get you up and moving a little bit, okay? So grab all your stuff, and here are your new groups. So just somewhere in the room, find a spot. Hey, I'm here. Let's go here. Figure it out. Let's do this in 3 minutes or less, please. Bring all your stuff. Let's do it. I was going very fast. That would be you, because it's in alphabetical order. That's you. That's you. Sorry. You know what? There was one. I realized there's another name. Find a spot. Let's get it done. Don't bump the camera, please. There are front ones. We need groups in the front as well. Don't worry, you don't have to present like in front of somebody. You have to talk. You don't understand. Okay, so here we go. This you have on your sheet. Okay. It's on both sheets, actually. This is a very, not famous, but very well-known, if you're in chemistry, kind of a chart of ionization energy. What it's showing, you need to always understand graphs and charts, is that this is showing that its greater energy is going up, right? And as I go, this is just atomic number. So this is basically the entire periodic table, or all the way up to element 86. So what's all on top? What are all the purple? What are those? Those are noble gases. On each peak, are those the easiest or the most difficult to remove an electron? Like kind of as you go. Most difficult, right? But as I'm going, what's happening to them? They're decreasing, right? So, but these are the more difficult ones to remove, clearly. Like they're the highest ones. Why are they getting easier to remove, though? What's happening to each of them? Just a general, you don't have to be eloquent in your answer, but
they're getting further away.
Further away, right? The electrons are getting further away. But you're like, yeah, but the nuclear charge is a lot larger. True, but you're gaining all these energy levels, and you're gaining all this shielding. So on the bottom, what are all these? Those are my alkaline metals. Those look like they're the easiest, right? Yeah. So those are the easiest to remove. We're going to discuss all that. It is not, starting right now, what's a general chemistry answer that you could say? What does this do? It loses 1. Why does it lose an electron? right? Like all of these, you'd say, oh, they lose one electron to, what would you say? Now you're like, I don't want to say it because I know it's wrong. But I thought it was right. What do? They lose one electron. Anybody? No statement? When they lose one electron, they look like a noble gas. They lose an electron because then they become stable, or they lose an electron because they want to be looking like a noble gas, or they want an octet. Are any of these things sound like maybe something that you learned?
Yeah.
It's things that we told you last year. Kind of like parents tell you things, because like my kids last night, or 2 nights ago, they had flu shots, and we didn't tell them until we got there. I regret it now, but at the time, it seemed like a good idea. One of them heard, wait, what shot? I'm like, what? Me, I'm getting one. They handled it very well. We're going to talk today. None of that. Atoms aren't like, man. They're sitting in the break room. They're like, man, I wish I had an octet. And then they're drinking their coffee like, man, me too, man. I just wish I was stable. Yeah, I just totally do. Like, they're not doing that. So there has to be an extra reason. And that's what we're going to do today. So in your groups, okay, I believe on your back, I have little areas. We do 4 little spots here. So N versus O. Already, this is not the trick. What I love about AP questions, it's not like, hey, which one is greater? Most of the time, they'll already say it. So clearly by this, it's already saying that N has a greater ionization energy than O. Okay? Now your reason is explain it. You're not in the group for this. You're in the group for the next one, but I'm going to have you come in and out of this in talking about it. So we're going to actually physically do this together for the first couple. So what I'd like, and this is suggestion, but this is what I'm thinking, is that these are the ideas that you need to think about. So this is of nitrogen, this is of oxygen. I'd write those next to it. Like this is the last of the electron configuration. Okay? Just like kind of write them by each. You need to have an understanding of what's happening with the actual electrons to be able to have an actual discussion on this. So, what is it saying? It is saying that it is easier or more difficult to remove an electron from oxygen. Let me flip the script. Which one's easier to remove? Oxygen. Yes. Okay. That's the trick of this one. And these are all the scenarios that will come up, so I'm giving you every one of them. Electrons are negatively, positively, they're negatively charged, right? I know we pair them up, but Hund's rule says that they all are separate in the first place. One of the big reasons for that, besides being evenly distributed, is that electrons are all negative. Opposites attract. So negatives would repel. So I'm not saying they don't want to be by someone. What I would say is that electrons naturally repel each other. So, and you might want to circle it. This is the electron that would be removed. This one is the one that's going to be removed. Why is this one so much easier to be removed? Because it's lower. And I'm verbally saying all this. I'm not writing this down today. Electrons naturally repel each other. So this electron would be easier to remove due to the natural repulsion of the electron pair. They are at the same energy level. So I can't talk about energy levels, okay? I'll let you write that down, and then I want to talk about some things you cannot bring up. You have to find the one thing that makes this make sense, because everything else doesn't. I will say this again. Electrons naturally repel each other. So due to the one pair, that one electron will be easier to remove due to the repulsion. Like they're sitting in there, and they're already battling, they're fighting each other. They're trying to get as far away as possible from each other already. So that electron is easier to remove. Here are the things you can't say. What can hold in electrons? Nuclear charge. Which one has a greater nuclear charge? Oxygen. So you can't be like, oh, because oxygen has a greater nuclear charge. You just destroyed your argument. Because you can't bring that up. You're like, yeah, but isn't that important? It is, but we already know that this is easier. So that can't be the reason. So you can't bring that up. Is oxygen smaller or larger as I move across? Smaller. Okay, Mr. Blackford taught me something really funny last year. And you guys, if you took chemistry last year, you did see it. The snowman. If you remember atomic radius of the snowman, It gets larger going down, it gets smaller going across. But you have to know, this cannot even be a hesitation. It was a little scary when I asked which one was smaller or larger, and half your faces showed me you didn't know. You got to know that they get smaller. Why? The nuclear charge is getting larger as I go across, so it's shrinking it because it's on the same level. I'm not gaining levels when I'm on a row. So you can't bring up nuclear charge. You can't bring up size. So that's why. And these are very unique situations. I'm giving you the 4 that I've seen the most come up. And then you're going to answer some actual questions here. Okay. Next one. BE and B. What do the final electron configurations look like for that? BE and B. So like the last one, this was a 3s, a P3 and a P4. So isn't this an S2 and a P1, right? So that's the B, and this is the BE. I'm mirroring it with whatever's on top. So that's the BE, that's the B. I'm trying to give you a visual of what we're talking about. You need to understand where electrons are existing to be able to discuss this. So, this one's actually not overly complicated. Why is the B easier to remove an electron? Which electron am I going to be removing? That one? You always remove the outermost electron. By the way, this is further away from the nucleus than these. No, they're on the same energy level. Each one's a little further away. S, 1s, 2s, 2p, 3s. They're all a little further away. So that's the one I'm going to remove, and then one of these I'm removing up here. Any thoughts? I've already given it away. Any thoughts of why this one's easier to remove than one from the BE? Marco?
Like if you removed it, you'd have a full energy level?
Well, you'd have a full sub-level, right? And I appreciate it, but what if I say, so what? Like, the problem is with that, and we're going to have a lot of things we're going to say, and we got to make sure that we're saying it right. I hear what you're saying. The problem is, I don't know where else to go with that.
It was farther away from the nucleus.
It's farther away from the nucleus. Good. I'm glad you said that though, Marco. Never about reaching something that is a full level will be the right answer. It is about nuclear charge. It's about distance. It's about how strong something is being held on or weak to the nucleus. It's the relationship of your electrons to your nucleus. However you want to think about it, you holding on to something. Why is it easier or not? That electron is farther away from the nucleus. Done. Can I bring up nuclear charge? No, it's got a greater nuclear charge. That ruins your argument. Because you say N has a greater nuclear charge. Oh. So you're saying it's harder to remove now? No, I'm saying it's easier. But nuclear charge, your argument whenever you bring up nuclear charge should be that it's holding it in. It has a stronger pull. Okay? All right, let's talk about another one. Zn and Ga. Do I have that on that one?
GA is not on there.
Yeah, I had to write it on.
Yeah.
Because I just, it's right here. So that's Ga, and that's Zn. Why is that one easier to remove? Just looking at it right away. Why is Ga easier?
Further away from the...
Further away, and I'm going to add something else. The other one has this too, but what's all in the way from the nucleus to that last electron? Look at all that, right? So what else could I use? What's another term I should throw out here for this one? Now, the other one has this too, but this is severe. Let me just say, if I take that electron, what's in the way? Here's my nucleus. I have 1s, 2s, 2p, 3s, 3p, and then 4s. Here, I have all that, and I got 10 more. So what's the term I should be throwing out? Shielding effect. Due to the fact that the electrons are further away, and here's a good way of phrasing it, and there's an increase in the shielding effect. Okay? The electron in the 4p is further away, and there's an increase in the shielding effect, which makes the electron from the Ga easier to remove. It's always about easier and more difficult. You never say want. You never say making a full whatever. It's either being held on easier or it's being held on tighter. Right? There's a stronger pull or there's a weaker pull. And because of that, what we've done, I mean, I read books that say they want to be an octet. Like, my mind just blows up. Like that, we're writing that in a textbook. I just read something that somewhere in like some Carolina, they're teaching that the Loch Ness Monster is actually a dinosaur. So dinosaurs still exist because the Loch Ness Monster is a dinosaur. And that's their bridge, and I'm not getting into this, but that's their bridge to talk about why evolution doesn't exist, because dinosaurs are still alive. That's what they're going with, because the Loch Ness Monster. The Loch Ness Monster. You know why? Do you actually know what the Loch Ness Monster is? There's currents in Loch Ness, this lake, and it caused big chunks of muck and things to come up and rise and move, and people would always just see that image, and they always thought it was. If you never knew that, found that out. That's kind of a cool thing, and it happens every once in a while. There's these currents that cause it to happen. It's a dinosaur, though. One more. NE and AR. So, and I'm not picking on Marco, but I just want to keep using it because someone's going to do it. Someone in here is going to do this. Well, they're both full octets. I don't care. I don't care about octets.
We have AR and K.
What?
We have AR and K.
Oh, come on. Do you? Well, that's lame. Well, let's change your K to NE. But NE is greater. If I did AR and K, it's the same exact answer again. Why? It's further away in greater shielding effect, right? It's one more energy level. You're at one more energy level, right? From here to here, why does it drop so quickly? Because I went from here and I went out one more energy level. And then that means all this other stuff is now more shielding. But let's talk about this too, because, well, that's what I have down. So we're going to do it. They're both really difficult to remove. The reason why noble gases are difficult to remove, not because they have octets, is because they have the greatest nuclear charge on that row. Right? They are the smallest possible atom on that row. Right? Every one of them shrinks. There's no more increase in shielding when you're moving across. But, and I'm still repeating it, but why, and if you're like, why are we saying the same things? I'm trying to hammer something home if you haven't figured this out yet. Why is AR easier? Let's do it the other. Why is NE more difficult? Why is NE more difficult?
Closer.
The atoms, the electrons closer, right? And there's less shielding, if you had to say it that way. Can I talk about nuclear charge? I can't, because AR has a greater nuclear charge. We're going to put this into practice. This is just generic examples right now. This is giving you the ammunition, though. The next questions will be very similar, and sometimes I've used the exact ones, on your test. That's actually a mind blow when I actually will pull one or two exactly from one of these things, and it doesn't look so good sometimes. All right, so, there I was. I was ready. I just did 5. We don't need to do it, but this is just a good visual. See how you have one more? So just good to see it. If you're talking about removing this is all the stuff that's in the way. You got these 2, you got these 8, and that's it. You're removing this one, you got these 2, these 8, and another 8. You've gained 8 more electrons between you and the nucleus, which makes it a lot easier to remove. Okay, so this is what we are going to do. I'm going to assign you a simple letter, and you're going to work on one. Now, don't fill it all up because we're all going to be writing them as well together. But I want the groups to work on just one letter here. So is this one group? And this is one? Okay. 1A, 1B, 1C, 1B, 2A, 2B, 2C, 1A, 1B, 1C. Okay. First, work on your problem, okay? If you want to work on some other ones, that's fine, but really try to figure out no more than 3 sentences. My goal is 1 to 2 sentences. So this is the first 4, and then I have another 4 up here. But for example, potassium has a lower first ionization energy than lithium. You need to explain why. Like the statement is already telling you, you now need to explain why. I'm looking for words like nuclear charge. I'm looking for distance. I'm looking for shielding effect. I'm looking for energy levels. Like these are terms that we need to come up with. No wants, no complete octets, no complete sublevels. Right? Figure out what ammo you need to come up with. What statement are you going to say that answers this? You are going to have a chance to write other ones down, all right? And I have the answers that come up for the first 4 as well. But I want to see what we come up with. So give it a couple minutes. Let me give you 3 or 4 minutes. Come up with the answer you feel good with from your team. Kind of talk about it. Figure out what you want to go with. If you guys want to break it up and see if you come up with different answers.
Yeah.
I have no clue.
I just don't know. I was gonna say
Could it be because nitrogen has 1 less proton? To pull it closer. No idea.
It did have an extra, or 1 more electron. Or an extra electron.
No. How do you say like the electron?
The same number of electrons. Yeah, I think it's because nitrogen has 1 less proton, which the protons pull the electrons in closer. Like, has 1 less proton.
So O2 minus is easier to get.
It's asking which one is larger, right?
Yeah.
Then what I'd like you to do, if you are done with that one, what I'd like you to do is start going through all of them, and just with your group, just come up with a key word, like, oh, it's because of this, or it's because of that, okay? I want you to make a little note next to each one, so you're going to be writing like greater nuclear charge, or, smaller atom, or greater distance. I'd like you to come up with a key word, not in a full sentence, together. Go through all of the other questions just on the side. I just want a simple statement of, like the little word, what's the key word before we go through the official answer that each group gives, okay? We'll do that as a team. It's important. This is why. This is why. This is why. So do it together on every problem, but you're not writing your answers out yet. Just do it on the side, okay? But I'd like you to try to do it together. That's the whole point why you're together. You have to use your other sheet to kind of see a visual, that's okay. We're looking at your table.
I said nitrogen has 1 less proton pulling the electrons in, so it's larger.
Please, groups, work together. Keywords. Why is it this? Why is it this? Just what comes up without doing full sentences. I want a full answer. We'll come up with those sentences.
I think it's electromagnetic.
It's
easier to read.
Oh, it's across the period.
Yeah, look.
What did you for C? What did you for C?
What?
Selenium.
C? I would go with the same reasoning as we put for B type deal.
One of them might be a repeat.
So
of what we
since
just did.
zinc has more shield.
Yeah, D is on the
That's
front
okay.
thing.
Believe me, it comes up a lot. Being oversaturated in this is not a bad thing. Okay, you may not be all done with them, but I was hoping that you put some keywords. So, 1A, anybody want a general idea? What do you guys got?
Lithium only has 2 electron levels, so its furthest out electron is closer to the nucleus.
Okay. Anything else? Where's the other 1A? You guys, what do you guys put?
Potassium has a larger atomic radius and therefore has a greater shielding effect on the outermost electron, making it easier to remove.
I love it. You guys went off of the lithium, you guys went off of potassium. Sometimes you can do both. Great suggestion. Now, what I'm about to show you does not mean that this is the only right answer. But it is also really important to make sure that you have set the table. You should, starting this point forward, you should really address both. You need to say what this one has and what that one has. Because when they give you 2 scenarios, potassium and lithium, like I did on the side showing the electrons, you need to have the reader know that you understand what's happening in both. So just before you start writing, just kind of paraphrase, but this one says potassium valence electrons is 4s1 while lithium is 2s1. Potassium's electron is shielded by more electrons than lithium and is therefore more easily removed at a lower energy. This, I took it based off of the potassium. You could definitely say it the other way. The reason why I chose to do the potassium is that that's how the question was stated, not that you have to do it that direction. I would suggest, if I were you, is to paraphrase. I wouldn't necessarily write it completely word for word. Make sure you just get the general idea. Okay? As I move down, it's not about, oh my gosh, never say, well, according to the trends, as you move down the table to the lower left, it gets lower ionization energy. No, that'll never be good enough. You know, like when we do our arrows, you just say upper right, lower left, not enough. You need to actually have an explanation. So, good, both teams, I think you got it right. It's always interesting that people go different directions, which is exactly what I expect to see though. All right, this one's a little trickier though. The ionic radius of N3 minus is larger than that of O2 minus. What did you guys come up with? Anybody?
We said that since they have the same number of electrons, but nitrogen has 1 less proton to pull in the electrons closer, that nitrogen is bigger because.
Okay. Where's the other 1B or 2B or 1B? Don't we have another 1B? I know we do. Okay. What do you guys have?
We just kind of said because oxygen is a smaller atom and has a smaller atomic radius.
Okay. So it's smaller atomic radius, but now that would be okay if you were talking about just the atoms, but we do have to talk a little bit about those electrons. Okay, so we would need to touch on that. There is a term. If you could quickly for a second go to the other sheet that we have. On the back bottom of the other sheet, I have circled something. You do not need to use this word, but you need to, I'm going to use it in a second. I need you to understand it though. Isoelectronic. Isoelectronic is a fancy way of saying that all these ions or atoms have the same number of electrons. That's all. So, if you look at the periodic table with me for a second. If this was N3 minus, O2 minus, F minus, Na plus, Mg2 plus, Al3 plus, how many electrons do they all have? They all are looking like neon, don't they? All ions, when they become ions, will reflect the electron configuration of the nearest noble gas. Those are all considered to be isoelectronic, but they all have different number of protons. So it's always about nuclear charge. And I didn't hear either group, Mason, you overly explained it with the protons, but you could just say nuclear charge. This is much longer than it needs to be. It says the addition of electrons to a neutral atom, all this doesn't need to be put in here, produces an anion that is significantly larger, blah, blah, blah. Even though both ions are less isoelectronic, there's a greater nuclear positive charge in the oxide ion, or oxygen, causing its electrons to be more tightly pulled towards the nucleus. So the key to this, regardless of if this is confusing to you, the key to this question was the nuclear charge. Right? We're on the same row. If you're on the same row, nuclear charge probably be used. If you're going up and down in a column, nuclear charge should not be touched. because now you're gaining energy levels. Now that's about distance, okay? When I'm moving in the row, the reason why nitrogen is larger is because there isn't as much pull. Now you could go down the other road. There's more electrons in, you could say, in nitrogen versus oxygen. That's not right. It's the same number, but the ratio is different. You have more electrons to your protons, so that pull is spread out more. I've heard people do that. You know, like for every proton that's pulling an electron, it's spread out. It's not as good of an answer as nuclear charge. Oxygen has the greater nuclear charge, which causes the electrons to be pulled in tighter. And then what I would have said, even though they have the same number of electrons. That would have been my answer. Okay, so nuclear charge is the money word on that. Good. I'll leave that up for a second. These are the ones. You're going to have 3 or 4 phenomenon like this that you're going to have to try to justify. And it's all the terms that we're talking about right now. So I'm going to go on. Again, I'll just say my answer again. Oxygen has a greater nuclear charge than nitrogen, even though they have same number of electrons, which would cause the electrons of the oxygen to be pulled in tighter, which would make the atom smaller, or the ion smaller than the nitrogen. Okay, 1C, what do you got?
Zinc has a greater nuclear charge, so it would bring the electrons closer.
Okay. You guys want to see? No. No, what do you got?
You said calcium electrons are farther away from it or
Okay. All right. So let's talk about those two. So you're saying zinc, calcium is, zinc has a greater nuclear charge, so that's why it would be smaller, right? Is that, and you guys said that calcium's atoms are further away, right? Okay. Let's look at where they are. You're on a row. You got to think about rows. When I start adding these, where are those being added? They're being added in the 3Ds, right? Even though they're greater energy, and technically they'd be further away in a lot of ideas, they're still in an inner shell. You still got to think about inner and outer. They're not in the outer energy level. So why is calcium larger than zinc? As I move across, it's always about nuclear charge. Okay? I'm gaining nuclear charge. That's the only reason why it gets smaller. You're gaining nuclear charge. It's getting sucked in more and more. Again, way longer than it needs to be because it's just overly explaining. But you could say like the number of electrons are not being added from at a further distance, but the nuclear charge is increasing as I go from calcium to zinc, which causes the electrons to get sucked in or get pulled in tighter. Okay? And it says that somewhere in here. Pulls the electrons in more tightly and reducing its size. Nuclear charge. Boom. Okay? So nuclear charge is your money word again. So I hope we're already starting to see. As I move across the row, nuclear charge. That's my first instinct. When I move down and out the row, it's about distance, shielding, energy levels. That's where we go. And this is a huge deal. That's why we're addressing an entire large group to this. This stuff comes up a lot. As we're writing that last one, boron has a lower first ionization energy than beryllium. I know we just did this one, but I'd love to just hear it again. So where's my 1D? What do you guys got? Whoever wants to read. One of you four.
So because boron is okay, so it's gonna fall off more because it's farther away from the nucleus. That's more because there's less of a shielding effect, right?
You were doing well. Boron has a greater shielding effect. Because this is at S2, this is at a P1. So you have that S now in the way. Right? So you have more of a shielding effect. The electron's further away, and you have a greater shielding effect. So it's easier to remove. That's why. Okay? So what did I write? It said boron's last electron is 2p1, and it receives the benefit of the shielding, don't worry about effective, by its completed 2s, thus it is easier to remove this electron. If you want to talk about distance, you can. But shielding and distance would be where I'm heading on this one. Okay? I was with, at my AP conference yesterday, a AP reader that has been reading AP Chem Test for 5 years, and she kind of just reinforced a lot of stuff I kind of already knew, but she says, people elaborate. You write too long, once you say something wrong, they have to take something off. So don't say more than you need to. Also, don't just be like, shielding, distance, electron, gone. Like, you have to sound like a human as you're writing. Okay, quickly, 2A. So it says the second ionization energy of sodium is about 3 times greater than the second ionization energy of magnesium. So what is the second ionization energy? Maybe this is really hard for you. It's removing that next electron and removing that next electron. So it's called successive ionization energies as you keep removing them. So I kind of gave the two, this was a bit of a challenge. So 2A, did you guys come up with anything? I thought this was a little tough. You guys are 2A, right?
The sodium, you would have to take out their 3s1 and one of the 2p's, while the magnesium, you could just take the 3s2.
Yep. So, where's that? So we've established what that means then. So what I'm doing is I'm taking it from the 3s1 and then the 2p6. Here I'm taking it from the magnesium's from the 3s2 and the 3p1. So why is that one from the 2p6 harder to remove than the 3s1 from magnesium? That's what it's saying. Where is that 2p6? It's closer to the nucleus, right? The 3s1 has shielding and is further away. That second this is why, well, once it becomes a noble gas, it's stable, it's happy. No, it got that much closer to the nucleus and it's harder to remove. I have answers on the next page for this. I will show that all in a second. We'll talk about it. Magnesium, you got the 2p6, you got 3s2, 3s1, and now you're here. Sodium, you're at 3s1, now you're here, and now I got to try to remove one from that lower level. 2b, the difference between the radii of Na and K is relatively large compared to the difference between Rb and Cs. Any thoughts?
So we thought that RB and CS are going to be farther down, so they're going to have more energy levels in the shielding effect compared to Na and K.
Okay, so the difference between, right, is relatively large compared. It doesn't mean that this is large compared to this. Like this is greater, this is less. Exactly right. As you start to go, what else do you gain between these versus these? What other sublevels showed up? No, the D's. So from here to here, there's no D yet. Here, you're gaining 2 D levels. So this has extremely increased shielding effects. So it's going to be a much larger atom from one to the next than between the other two because of a much greater shielding effect due to the addition of D orbitals. Lastly, where you guys? Says a sample of nickel chloride is attached in a magnet. Oh, shoot. Did you even?
We have a couple.
Go for it. Whereas a sample of zinc chloride is not. Any thoughts? We did not talk about this.
The zinc has more shielding effect than the nickel. Zinc also has more ionization energy, therefore zinc is harder to remove and will be less attracted to the nucleus in the magnetic field.
I appreciate the effort.
Hey, I got 2.
Yeah, he's got one too.
I have some more.
Yeah.
It would be.
I need to address it.
Okay.
I'm gonna stop you. You need to write this down on the side. I totally forgot. We will talk about this tomorrow. When you are attracted in magnetic, this is easy. It's not actually complicated. This was nickel. Or this is nickel. This is zinc. When you have unpaired electrons, that is what is attracted in a magnetic field. That's it. Unpaired electrons. That's it. I'll say it again. If ever it comes up, and I'm sorry, if it ever comes up and talks about magnetic fields, the one that is attracted, it's not about charge, it's about unpaired electrons. If you'd like to take a photo of these answers, you definitely can. We will talk tomorrow. Hey, from now on, I figured out, guys, when we're using the LabQuest Pros, it syncs right up to your iPads. So you get the graph right on your iPads as it's happening live. Pretty sweet. So start having your iPads. I'm going to start giving you things that you need to download and stuff. But that'll be more next chapter. But I don't have time to sneak that in now. So, now on for reviewing for Tuesday. Thank you.